like we said, the SAT has some common themes to it. So just in math in general, what you're always going to see on the SAT are your quadratic equations, so parabolas. You want to know everything there is to know about quadratics. You're going to have your linear equations, which are more fundamental, more logically. I put the linear ones first. That's your y equals mx plus b, slope, any of those kinds of things, x and y intercepts. And the other big one that shows up is exponential equations. Not as much as the first two, but the first two are definitely our bread and butter. And I would imagine that anyone who's studied for the SAT has already put a little work into those, and more can always be done. But for now, I'm going to focus us a little bit on exponentials. The idea of an exponential equation is that you've got your y equals, just like any other equation, but you've got your starting amount and the thing that you're multiplying by, and you're doing that x times. So whatever we're starting at, whatever we're multiplying by, and you have the number of times that it's being done as the x. So mathematically, this is really unique to have in an x and y situation. To have x in the exponent is not where we want to see it. And not to nerd out too much here, but that's the basis of logarithms, is the way to kind of get x out of that spot. You don't need that for SAT success, but just a little background info there. And so one thing you always see with exponentials is percents. So, just as a quick sample before we get into the practice problem, if I had something that started, let's say that I started with $50, and I'm going to increase that money by, it's, let's say my childhood savings account, we're going to increase it by 15%. And X represents the number of years that that's going to happen. So according to the exponential equation, the amount of money you have is going to be equal to the starting amount of money. And then the thing you're multiplying it by, now there's this inherent kind of involvement of percents here. With percents, you start at 100%. And if you increase or decrease by 15, it would go up to 115 or 85. And when you go to use those mathematically, you need to put them in decimal form. So 1.15 or 0.85. So what we're going to multiply by here is the 1.15, and we're doing that X number of times. So with this equation, we could solve for what would happen after 7 years, and X would be 7, and something like this will most likely show up in the calculator section, where you can really do 50 times 1.15 to the 7th. So anything to add, Patrick, before I continue?
Yeah, so I think that for the decay functions, which are a little less common, this is if you were to grow your money. So for the decay, as you obviously said, from the 100%, you would have to subtract your 15% to the 0.85. Usually problems with money and those kinds of things are growth. So you'll have the 1 point, which represents the full principal value plus whatever percent that money is going to be growing at to the power. And then for the decay functions, again, which I think are a little less common, usually involve something along like a radioactive substance, right, that loses a certain mass over time. Just keep in mind, as with all questions on this test, you need to read very carefully, but just keep in mind in those instances, you would be subtracting the percent from 100. But yeah, all awesome. The rest is spot on.
Yeah, and percents are different from other numbers because regular numbers start at 0, percent start at 100. So that's something that, as a
decimal
SAT
is one,
tutors,
correct. Small things, yeah.
Find ourselves talking to students about almost every day. So this would be one example of that. And Patrick, what I think I'd like to do is maybe do the 3 questions on exponentials and then scroll down to one of the ones that you had prepared, because we could very well spend the first 30 on this and the whole live stream is over.
That sounds like a good idea.
So we've got our equation that we mentioned before. Here, John is investing $1,200, growing at 20%. So we talked about the 100 going to 120%, or going down to 80% if something were shrinking by 20%. So here it's growing at 20%. So it's going to be 120%, which in decimal form is 1.2, and 80 would have been 0.8. So 1.2 right here, and X is the number of years, or in this problem it says T. So In this sample problem here, we were tasked to write an equation for this situation, investing $1,200, growing at 20% for T years. And this is what the answer would look like. And on an official SAT, you'd be asked what would happen after 2 years, 3 years, 5 years, and you would just plug that number in for T. So that's kind of like our basic setup for the exponential equation. And what can happen next, or what happens on some of the harder questions on the SAT, is that this is being offered to us every 3 days, and the flip side would be 3 times per day. So we're talking about a similar situation. You have the starting amount of 450. It's tripling, right? So this is not percents, it's just tripling. It's actually being raised by 200% for the fellow nerds out there. And if it were every day, that would be X, right? So this is our fundamental thing that we just talked about. But there are only 2 things that can be done with this. You can have the exact same thing being divided by 3 to the X over 3, or the same exact thing being multiplied by 3. So you can already see how on a real SAT, this would be the confusing question, one of them. So the one we're going for here is this one right here, every 3 days. And the way I think about this is just imagine different values for X. So X is the number of days, or D is the number of days. Actually, I should have used the letter D right there. Same difference. But in any case, if D or X were 6, then how many times would this activate? So if you had like a 6 right here, then how many times would this whole cycle activate, Patrick?
6 divided by 3, 2.
2 times. Yeah, exactly. So that's what we're talking about. Every 3 days means that as 6 days go by, this whole thing is going to activate 2 times, and that would make sense. Because if it happens every 3 days, in 6 days, it would happen 2 times. So
that's a very good point. Sorry, just jump in there. As you said, if you're unsure if it's X over 3 or 3 times X, because sometimes that's a little tough to see, plugging in some value of days, 3, 6, 9, I think that's a very useful tip to just think about it in that way, right? If you were to do 6 and it doubles every 3 days, or sorry, here it would triple for every 3 days. It's much easier to see when you plug in your own number, which is a very good point.
Yeah, and this is one of the more confusing little things that comes up, because even for a tutor to say, you know, I think you should plug in numbers here, it's almost like a backup approach, right? But to be honest, that's what I end up recommending to my students all the time, because yes, this is actually one of the more confusing things. And if you'd like more info, you can reach out to us. That's what we're here for, professional SAT tutors. We tutor students all around the world. We'd be more than happy to tutor you or your child. So for this one, this is the other idea, where it's happening a bunch of times per day.
Okay, yeah, sorry.
So it's starting at 350, and it's losing half of its mass. So it's being multiplied by 1/2, and it's 3 times per year. So if X is the number of years, it's not happening every 3 years. That'd be dividing by 3. It's happening 3 times per year. So like Patrick said, think about different numbers in here. So if it's happening 3 times per year, as 6 years go by, that means it would happen 18 times. And that is what would happen here. You'd get an 18 right there for 3 times 6. So the question is when to multiply and when to divide. And we're kind of thinking about plugging in numbers either on paper or in our mind to try to make sense of that. Anything to add, Patrick?
Nope, I think that's perfect. And then also just to add in, so here it's losing 1/2 of its mass. So as you see, it's not a percent. However, the value we have here is 1/2. So it's not a growth function, it's a decay function. Just add that part.
Yep, and this is equivalent to the same situation if it were being expressed as a percent. Sorry for my handwriting there. Then in the parentheses, we would have the same percent that goes with 1/2, which is 50%.
Just to ask you a question, if there's maybe students out there, if it's expressed as a fraction inside the question, you prefer your students leaving it as a fraction, just as if it was expressed as a percent? You think it's better to leave it as a percent, or is there one that you would prefer working with?
Generally speaking, whenever possible, I encourage my students to use fractions and not to use their calculators, even on the calculator section. We find as tutors that people tend to be so calculator dependent that they're leaning toward a tougher way of doing easy questions, and why not do it the easier way? So you know, it's funny how everything turns on its head when you get to high school, because all the same things that in middle school we say, oh, I don't like fractions, I don't like this, I don't like that. In high school, they become your friends. So yeah, whenever possible, you want to lean toward fractions and you want to lean toward doing things by hand, because it's a lot easier to make a mistake, in my opinion, on a calculator than on on paper.